Actually, लेकिन ऐश्वर्या को मैंने बोला था तो taxi कैसे book करोगे? वो कुछ वो वाले just have to make sure कि वो वापस लेके आए.
Very nice.
Right.
So he joined.
No, he's joined it actually. He's done an international book. International book. And he joined it.
I have to ask the department how was the so it took so many things to
Yeah. You should have had such
What now? She wants his.
Check me and email and then
Can't give a like. Yeah, one of the.
I think the plan would be that you can either work on the Davis complex exercises. You want to, I think, yeah, it's hard to follow when someone's just like telling you do this, do this. So if you want to understand this, examples would be great. The there's an example D5. I think that should be easier to draw compared to the other ones. So I would recommend that you think about that. Or if you didn't like this stuff, you can go back to the geometric reflection groups section. So there is an exercise about trying to classify two-dimensional geometric reflection groups. Now, so basically, like one part of that would be telling which triangle groups are spherical, which triangle groups are Euclidean. So you can try that exercise. And then, as before, Aishwar, you can ask Aishwar and I any question if you have. We'll just be able to. So maybe we can do this until like we can do this for half an hour, and then I'll wrap up. I'll just like I'll quickly tell you how to prove calculus. I have to do the full proof, but I can at least give you some glimpse of how it's done. So maybe last 20 minutes. I'll try to summarize. That's so far. Yeah. Okay. As before, you can discuss. You don't have to sit alone. Also, if you need help getting started on, if you're thinking about the Davis complex and need help getting started, then also you can ask.
Right. Right. But so, so I think you should kind of look at master day.
This, I'm not able to. This.
Okay. Some strict data. Strict variances. And 0.8. Handled by them, but the child. As a contract. I guess probably fair. But then, images are something compared. It's age. So you have to telegraph age, telegraph of customer what else.
That people specifically read different things.
I missed that part. How are you? You mean to say nothing? Right. No, we were talking about it, Just the fee.
Yeah.
Yeah. And he said, by the E, identity,
Yeah,
okay, yeah.
And cost of some.
And that will be the whole question. So then, here, let's run the example.
So controlling this first one, WI, WA, these are the spherical subs. So that will lead to construct.
Right, right.
Yeah. So I was doing some.
Which.
Try.
But I'm going. That's not my direction. You played it. And what's the to volume? This will then. You can handle the whole election.
Yourself will always be this, right? The coset of W5. The elements of that. That means the elements of W itself. And when you have a edge, that becomes a complicated pattern, and that will become. You take W by W edge first.
Inclusion of what we want. Means like here the portions are associated with this portion is connected. That's portion.
Yeah, but.
No, I'm talking at the very beginning part only, not till there.
Okay.
Yeah, yeah, what is the inclusion of what it was? Okay. Big, yeah. Contain or may not have any relation.
Yeah.
Okay.
If one is contained, we just.
Draw a line, a smaller one.
Not direct.
So there is no direct. So therefore, but here then you have what? You have W is the biggest force, right? You have map of SW5 to W. If you have all the vertices, you map to W. Yeah, all of this will be the edges. But these are not vertices, right? SWT is not a zero set. The vertices are only SW5, STW5, STW5. The green one for the one. You will have SWT also in the vertex.
After the rings.
Recellulation, you have the final picture. Starting point, you're taking all the supports.
Not all the circles. Yeah, in this case, all the circles.
Yeah, but sometimes it might get identified as what you. Oh, that's why the WT is very. So WT is the cosets of T inside W. The T is a super. Or a generator.
We already have that explanation.
Right.
Yes. How? Circles.
In some sense.
And we are not. Particular evidence. It is those substitutions.
Yeah, keeping you will see for those are still substitutes. And he said.
So you can have S comma T also. For example, S square to T square, that is T, A square to yeah.
So that's the same. It could be equidistant triangle.
You're taking all the.
Barabar.
These resume development by W5, they have a
35. I am counting the center.
and if here you have which one is contained inside, you have like one thing is contained in every of them. So one is got some two.
So see road portion represented was there. And also
You have written the cosets itself. If you want to get a square will come down. These are the cosets. Okay, now you're saying that this is content.
If this one is contained, so this S is contained, so there will be a page from like how she wrote this and here one dot double. This is one dot W. So like one dot W.
One W5 is one W5 and SW5 is not good.
Yes, W. So this element is one W.
Yes, so that is the yellow.
Yes.
But it's not a new, it's just a midpoint, it's not a new edge. Why is that? Okay, that's just going up.
Yes, but these constructions fine, but when they will be glued together, those.
You know what is the number is substance. And how you get that? Oh, so this one I understood you have the vertices for each complex. So if here now WS is considered important, this WST is content. So WS will be mapped to this whole one dot W, right? This is one dot W. And WS is not going to do any of them. SW5 is.
Yes,
Yeah, but it's. And SW15.
so one, two, and this three.
We have. This is like a telegram. WS.
Yep.
No, that is a redefinition. That is a redefinition, okay. Next you have. Or
So the.
Yes.
So, basically capture all those.
Yeah.
Suppose there is
So this is done then.
this is one space where our posture book will be included. So much preparation. Just interval, so these two is the inner portion like the end of social planters. So there will be two how many. Sorry. 1, 2, 3, 4, 5, 6. 6 will be there.
Now, how you get this 100 over for that?
So what happens? So the region between this reflection line and this reflection.
Oh, that will be the, yeah, because the coxeter here. The geometric represent, what is that?
That comes with the,
That is,
I mean, also the real line.
So the map code is real line or Laplace first. Interval or Laplace.
Another means like I have two coastal elements. This. The coastal element will take them like two in that way. It will not take one element, some other element in that region. It will permeate between those domains.
There's action when you
Means the action which we are defining. So it's
From to this have to be
X
for S,
sheet also.
and they have to be equal.
So like
So those are two numbers.
when we are giving the rotation,
From 0
so it goes to that
So ABC,
point.
because
So
it has a two
SX. When S is applied,
So I will
take the
call
point
yes,
X goes there. Then when the reflection.
And now, but this is all.
That element means T acting on
This
SX.
cone was an
Then
element.
comes to the next domain. And so
Then
when
I
so this
want
becomes
the
the orbit of that
vector,
point X.
Which would give me the
And since
distance
the
of P.
we
Where the
the
Z
definition itself
I have
was
to
considered
consider
as.
And I want the distance of this field. Am I correct?
Oh.
That's how I'm choosing, so whatever vector. I choose.
So the P is a part of
I'm
the
choosing
working nice.
I'm choosing a vector for S.
Because our
Like,
our space
S dimensional,
is splitted.
but I only care. At a time. So these cells correspond to these are N cells, where N is the size of theta. So these are, even though I'm choosing the big S dimensional vector, but I only care about subsets which are T dimensions. But I'm choosing the big vectors, but I have the systems. Right, so from here, how do I reach the metric? So now. Yes. Distance between A and B. Yes, what's the distance? Double of that number that I chose. And what's the distance from P to
This collection.
double of that thing? And now if you keep reflecting, you'll just like, you'll see these same edges. So the, what's the metric on that? Two S here, two D is here, two G here, and then same number will be obtained. So that's the metric on the hexagon. I've given, I've told you the side lengths of the hexagon. And that's basically memorizing the hexagon.
Yes.
Yes, very good.
So this is really.
Even I actually got to. Last line,
Last
is
line.
what I missed.
This whole lake is without the.
If you're not used to thinking about geometry. No, it's.
So. Whatever is free, is not considered. I think that was.
Link to the cat one space. Link like this. Are you going to link?
We don't take the.
So this is finding. But you need it for the whole base. Can do without it.
Okay. Do you remember that? That is the links.
Here we can see it through the graph notion, like link is, the link for this point is for what are the incident versus.
S and T is fine, but how you get this is. This one is discounting it. How you see that?
The corresponding spherical circle.
Like you, because you are getting WS quantity is the whole space. Getting WS quantity is the whole space.
Once we know this space, like, we know what's the link, but otherwise, it's show for a vertex. It's not it. That one.
Link of every vertex L comma is that one. And that need computation. And then how do you paste the feelings?
Please.
There's no, I mean, you, Hollywood. Or you just recellulate, that is the thing next.
Should we? We had to wrap up. I think I'll just say a few things.
Yeah.
So, okay, so if you were thinking about the Davis complex, like trying to construct the Davis complexes, Cashin, I mean, these are the exercises I gave, Cashin solves them and helps me. So I would say don't look yet, but if you try for long enough and you want to check your answer, Cashin has nice pictures in his notes. You can check.
What is the spelling? Like,
Cashen, Chris Cashin. He has notes on Coxeter groups. So you can double check your pictures with pictures he draws. So let's just summarize how we've been doing and then end with. Just a glimpse of some applications, what Davis did with this
so
construction.
you would consider groups. Okay. And that is your PhD. This question.
So we have our Coxeter system. And then we have, let's Davis complex. And so I guess these were exercises that sigma is simply connected. No, you would like to say a word. So why is sigma simply connected? Because for simply connected, this is following from the fact that the two skeleton was a Ke2 complex. And very roughly, what's Ke2 complex? Ke2 complex is you take the Ke graph and then you fill in 2 cells for all the relators. In some sense, you're killing the loops that are coming from the relators, and then you have to argue that you've actually killed all the loops. So you have to prove that the Ke2 complex is simply connected, then the space is also simply connected. And this action, the Coxeter group acting on the Davis complex, is properly discontinuous and co-compact. This also is co-compact. I think if you think about it, the chamber, like I defined this subcomplex called K. That turns out to be the fundamental domain. And that was a compact thing. And properly discontinuous basically follows from the fact that, so one observation you'll make here is stabilizers of cells by construction are finite. Right? Each n cell corresponded to a finite Coxeter, special Coxeter subgroup. So the stabilizer of that cell is a finite subgroup of W. The stabilizers of all the cells are finite here. And when you are in a polyhedral complex, when you're in a cell complex, that's enough. So that's the lemma you would have to prove to prove that it's properly discontinuous. The punchline is that cell stabilizers are finite by construction. So why is that enough to say that the action is properly discontinuous? It's just a general lemma that you have to if you try to. Okay, so we already have these two things. Now the theorem was that sigma is cat zero. The theorem is, so this is Mouson's theorem. And I should say historically, so Gromov proved, so if you look at something called a right-angled Coxeter system. So if you look at right-angled Coxeter system, this is the one where MST is always 2. For not always, it's either 2 or infinity for S not equal to 2. So only those two numbers are allowed. So these are called right-angled Coxeter. And you'll see it's right-angled because if it's 2, then you get squares. So Gromov proved that if you have a right-angled Coxeter group, he came up with a cat zero space. It was not the Davis complex, but something similar. And he came up with a cat zero space for these right angle coxetal groups to act on. And then Musong in his thesis, Musong was Davis's tool. And his thesis is, yeah, it's like, he just proved this like really awesome result in his thesis. So in his thesis, he proved that this thing was cat zero. So let's recall, so I just a very quick glimpse into how would you go about this? So this was the theorem I was writing before lunch. So this space is cat zero if and only if it is simply connected. So we already have this. So this was the girth condition. There was a girth condition, right? Like there should be no loops of length less than isometrically embedded circles of length less than 2 dk. Here it's simply connected. And the other was that sigma satisfies the link null. Satisfies link condition. What does link condition mean? That means the link of every vertex is cat1. So what's the link here? The theorem which was written here told us that the link of every vertex is this LWS complex. Basically, I'm claiming, and all I need to do is check that this link is cat1. Okay, so but when I say all I need to do, it's not that easy to check something is cat1. Okay. Like for example, let's just do a quick example here. Let's say I have these three squares glued together. Okay, so this is a M0 complex. If I look at the link of this vertex V, so just think topologically for now. Of course, I'm supposed to, this is sitting in R3, so everything is nice. I'm supposed to take a sphere around this vertex and see how it intersects my cell complex. Okay, so it intersects these edges in points, and it intersects each of these two cells in these arcs. Okay, so that's the link, and these are 90-degree angles. So I'm going to assign them length pi by 2. Okay, so the link here, link of B is this graph. It's the graph, not the filled in triangle. Okay, and I want to check, is this link cat1? Is this space a cat1 space? So what do I need to do? Just like recalling the definition of cat1, I need to write this. I need a model triangle, and if I am doing, there definitely is a triangle on the sphere. With all side lengths pi by 2. I can very easily draw such a triangle. So this is my comparison triangle. If I just take these 3 points in my space, this is the comparison triangle. And now if I take P here and Q here, and then I go the same P prime, Q prime. What's the distance between P and Q on this graph? It's I have to traverse it on the graph. So it's like, let's call this X, let's call this Y. That's X plus Y. This is X, this is Y. But what's the distance between P prime and Q prime on the two sphere? The geodesic between them is somewhere here. And so this is, so what I would be, if this was Z, I would, if cat1, if the space was cat1, then I would be saying that X plus Y is less than Z, less than equal to Z. But that destroy, that's a contradiction, because that's the opposite of triangle inequality. So that's a contradiction. So this is not cat1. This at this vertex, the link is not cat1. And yeah, last time, before lunch, I was saying, like here, this would mean it's locally cat0. And I want to say, just giving you intuition that if I've glued three squares together at that vertex, I'm not locally cat0, right? There is that positive curvature. Because that three that 3 cube is not there. I'm just looking at the corner of a square, of a cube. I'm looking at the corner of a cube without the 3 cube being in there. So that's some kind of positive curvature there. And that's being, yeah. Somehow the link not being Cat1 is capturing that this space is not locally Cat 0. It's locally Cat 0 at other points. Like if I take a point in the interior of this 2 cell, then it was already a Euclidean 2 cell square. So there it's locally Cat 0. But at this point, somehow it's not locally Cat 0.
Which is cat one, right? Locally cat.
No, no. Not locally Cat 0. Locally Cat 0 means the link is Cat 1. You have to go like,
Okay.
yeah. So the link is not Cat 1, so it's not locally Cat 0. Yeah, you somehow have to go to the link.
One dimension higher.
And the link has lower dimension. Yeah. Yeah, so hopefully, yeah. So without going, this is the idea for why you need to check the link condition. Why it's enough to check the link condition. Or, yeah, how is that related? So if I have to check that this is Cat 0, I basically need to check these 2 things. Now, this is often hard. Checking if something is Cat 1 or not is hard. So the main one of the main contribution of Musong's thesis was this something called Musong's lemma. He tells us when is something Cat 1. And let me just write it. So 2a. So he says some space is Cat 1 if and only if L has if it satisfies both these conditions. Edges of length at least pi by 2 and L is a metric flat complex. So what does metric flag mean? Basically, if you see the one skeleton of a if you see the ones, yeah, this L is a metric space, this link is a metric space. And if you see in this metric space, if you see the one skeleton of a spherical simplex, that simplex needs to be there. So that's usually for flat complex, we say if you see the one skeleton of a simplex, that simplex needs to be there. I'm saying the same thing, except like I want it to be metrically true. I really want there to be a, not just combinatorially, but I want it to be metrically true. If there is a spherical simplex, an honest spherical simplex, whose one skeleton is here, then I want that simplex to be there. For instance, like this is not a metric flat complex. Because I have this triangle, which is a spherical triangle, but it's not filled in here. So this is not a metric flat complex.
It is not a spherical complex, spherical simplex.
It's not a spherical, yeah, it's not, it is a spherical simplex.
What do you mean by
It
spherical?
is a spherical polytope.
So what do you mean by spherical?
Spherical complex is the pieces are spherical simplices. Like this is a spherical edge, spherical edge, spherical edge.
Yeah.
But the one skeleton is here of a spherical triangle, so the triangle is missing. So it's not a flat complex. And which you can see, just because this was empty, that's why it failed the Cat1 condition. So you can see why Musong wanted this condition. If he wants the link to be Cat1, he wants this to be filled in. Where is this edges of length at least pi by 2 coming from? At least in general, it's hard for me to explain it quickly, but in the Coxeter group setting, it's coming from very roughly from dihedral. It's related to the dihedral angles of your Coxeter polytopes. Very roughly it comes from. It's related to that. But so what I want to end by. So Davis proved a lot of really nice things using his construction. So I just want to list a few things just to show you what all one can do. With these. And the fact that this complex is Cat 0 lets him do all these. Basically, through these construct these things which have nothing to do with Coxeter groups. So he creates a bunch of exotic. He has a trick called reflection group trick. So basically, what he's able to do is he's able to construct the first examples of closed aspherical manifold. Um, that is not covered by some RM. So what does aspherical mean? Aspherical means all higher homotopy groups are true. Okay, so this has nothing to do with Coxeter groups, but somehow he's able to use his construction of so like very roughly what he does is he first starts with a he first starts with a complex which is he wants to be the link. He carefully chooses a complex which he wants to be the link of his Davis complex. And somehow he's able to do some trick to change that Davis complex into a aspherical manifold. I don't fully understand this, but he's able to construct manifolds with properties like he can construct a closed aspherical manifold that is not residually finite. I'm not going to define this. This next one maybe you appreciate. He's able to construct a closed aspherical topological manifold that is not homotopy equivalent to a smooth manifold. That is not homotopy equivalent to a smooth manifold. These kind of questions people definitely care about, right? When as a topological manifold can be given a smooth structure and all. So he's able to use his Davis complex construction to do this. He also has a paper where he constructs, so this is different, not necessarily aspherical. He constructs hyperbolic 4 manifolds. And apparently they're not that easy to construct. Again, I don't understand this, but he uses Coxeter groups. The idea is you start with a Coxeter polytope in 4 dimensions. And then you could, you start with a geometric reflection group in H4, hyperbolic 4 place, and somehow you are able to get a manifold out of it. The reflection group doesn't necessarily give you a manifold by itself, but you have to do some more work to get a manifold out of that construction. What else? Yeah, and I think these right angle Coxeter groups, their Davis complex is a cube complex. So if you thought about the D infinity cross D infinity example, a cube complex is basically instead of like any random polyhedra, you have cubes which you are gluing together along isometrically along faces. And the fact that this is a cube complex and in fact it's something called a special cube complex. This showed up, this was important in there was maybe like now 15 years ago, this virtual fibrine conjecture or virtual Hapkin conjecture was solved. And the fact that this thing is acting on a special cube complex was quite important as a step in that. So I don't understand a lot of this, most of it, but it's just to say that Coxeter groups are very interesting on their own right. I think there's like a very rich theory. The part I didn't even touch was this connections to Lie theory, right? But even from this perspective of geometric group theory, you can use it as a tool to construct lots of examples. That's what I'm trying to say. It's a very rich group. I think I'll stop it. Thank you.
Anybody, any questions?
These questions and groups are also called parabolic, which is the reason follows.
Okay, sorry. Thank you for saying that. This has nothing to do with. I should put this in quotes. This has nothing to do with the parabolics. My bad. Yeah.
Now, it's in general, the notion parabolic, how it derived for those subgroups, why it's called parabolic subgroups, so that's.
I think even,
That comes from the Lee context.
yeah, even I don't fully appreciate why they are called parabolic.
Generating set S will always be finite for Coxeter groups or
I am only looking at finitely generated Coxeter
it need
groups,
not be.
but I think you can have infinitely generated
Yeah.
Coxeter groups, yeah.
But this yes is bad enough. Yes is bad enough. There's just so much of variety and so on.
Right.
So I think that's very difficult to analyze.
One thing I didn't even like touch upon is, I mean, I was talking about for a general group, you can have different generating sets, right? So for a Coxeter group, you can have, what if you have different Coxeter systems?
Yeah.
Like it's there's no reason to believe there's a unique one. So like knowing when is it unique, when is it not unique. So like I think there's an exercise for D6, for dihedral group 6. Can
No,
you
but
still?
that's just a very fundamental question. I think the examples that you gave, there are only few examples of that. You know, it's a very fundamental question whether they call this, there exists rigidity of Coxeter systems.
Right.
Yeah, and you know, that's a very actively pursued and many cases are known, but you know, it's.
Oh, it's not known in general. So there's an exercise which is just about dihedral groups, even among dihedral groups, which ones are rigid, which ones are not.
No, but I want to, how do you get this generic construction of cat zero spaces?
Are there any generic?
See, for example, if you take just a Coxeter group, you construct this Davis whatever and actually.
Right.
So are there any other, I mean, how large is the space, the set of cat zero spaces in comparison?
So one reason why people who study cat zero spaces like Coxeter groups, because it gives us a very natural examples of cat zero spaces. Yeah.
No, but that's not how Gromov started, right?
Yeah, Gromov started
But
studying
they-
this, yes, of course.
I think that these people before that, there's exist Coxeter groups exist lead to this, like, some examples of cat zero.
Right. Right.
What I'm asking is that are there any other generic, other kinds of things that come forth there?
I can't think of top of my head. But any polyhedral complex that you construct, you can, I mean, there are theorems about checking whether it's cat zero or not. These, the ones with the lake condition. I can't think of a nice triangle. I guess, okay, no, I can give you one natural example. If you look at, you look at hyperbolic 3 manifolds, which have cusps, like torus boundaries, then their universal cover would not be F1. But it would be cat zero. Because the boundaries will have these flats. So in the interior, it will in fact be cat -1 because it has the hyperbolic behavior. But the boundary, because the boundary has these flats, the torus, if it was torus boundary, then in fact the space would be cat zero. Yeah, sure. So yeah.
So all these things are not relevant at all for like this finite things.
Yes. Already, I think in the first lecture, I was saying how with this
Yeah.
quasi-isometry
Right.
notion that in geometry you really care about, finite groups somehow become points. So I'm mostly interested in, this Davis complex also is, I think, more interesting in the infinite. Finite
Yeah.
Coxeter groups, it will just be like some finite complex. Yeah. I guess Coxeter already knew what all the finite Coxeter groups are.
Yeah, that was it, yeah. So this approach is not like this relevant for access finite things. Really finite Coxeter group, that is quasi isometric to this.
Right.
So you,
Yeah.
that C you take, connect this take to this orbit. It's simple. Well,
So there will be higher dimensional Lewis complex also. So it's n greater than 2. I think you are saying high dimensional Lewis complex also.
Yeah. Yeah. All the examples I wrote down were two-dimensional, because they're easier to draw. But yeah, you can have it and put it in. Yeah. Thank you for inviting me. This was a good learning experience for me. No worries. But for me, it was a learning experience. I think I misjudged how much I would cover and how to do how to arrange the exercises with the material. Come on.
काय पाहिजे
I think I'll leave around
हे
the last.
दोन points मधलं हे याच्यापेक्षा लहान हवं
Yeah.
इक्वल आहे पण
Flight type. Like if my flight is like
I'm noted down your flight.
Huh.
Departure.
Actually my flight is at 3:30.
3:30.
So I should
Leave around 12:30.
I'll 12:35.
Even Monday is okay, right? Tomorrow is Sunday,
Ah,
and that's also good. And you can just have the lunch and go and party.
should be fine. Probably it's not a big area.
It's not. Okay. The international sector was much more crowded than the domestic sector.
So is it the same terminal or no? The international terminal?
Yeah, the international is the next side, that side of it. So it's same, smaller airport actually.
Also, I think Canada is more useful for going off. So I should have like. It's like a slightly.
Hi. हो रे
असू दे.
हा.